Okay, this first question comes from pretty early on in section 3.1 or 3.2. If you're looking for the name of the topic, it's called the Difference Quotient. So what we need to set up is a fraction with expressions in the numerator and denominator. So I'm going to begin. In the denominator we have an h like it shows, and then on the top right we're supposed to subtract f of x. Since f of x is a function, in order to subtract the entire function, that needs to be done in parentheses. So this is where we're subtracting the f of x. Now here f of x plus h. X plus h acts as an input. The input needs to go in place of x. So instead of 4x minus 18, that 4x minus 18 becomes 4 parenthesis x plus h minus 18. Now when we simplify, distributing to get rid of parentheses, we're going to have 4x plus 4h minus 18 minus 4x plus 18 all over h. Now if you notice, every term in the numerator that doesn't have an h multiplied with it is going to get canceled. 4x, negative 4x, negative 18, positive 18. So that leaves us with 4h over h, which is equal to 4. Okay, graphing a piecewise function. It's called piecewise, if you remember, it's called piecewise because the function is not continuous. There's a piece of the function here, maybe there's one down here, and there's just different pieces of the function according to its domain. So what I would suggest is at each piece of the function, make an input-output table or an XY table particular for that piece of the function. So for this piece of the function, we can't just choose any x value that we want like we normally do for a function. We are constrained here. Our x values have to be less than 0. Now I am going to let x be 0, even though x has to be strictly less than 0. The reason for that is the graph is going to approach 0 on this side, and then once it gets to 0 it's going to stop. So I need to know the value of the function when it approaches 0, and then we're going to put an open circle there because it doesn't exist. If x is 0, 0 plus 1 is 1, so at 0, 1 there's an open circle. Open circle means the point doesn't exist there, but that the function comes up until that point. Now we're going to have to choose another x value, and because x has to be less than 0, we're going to choose negative 1. If x is negative 1, if this x right here is negative 1, negative 1 plus 1 is 0. And if we want to choose another one, if x equals negative 2, negative 2 plus 1 is negative 1, you can see that this is starting to form a straight line. It's only graphed to the left because the domain says x has to be less than 0. This piece of the graph is where x is less than 0. Now, for this middle piece, if we make an input-output table, this constraint right here, x is between 3 and 0. This is a bounded, x is bounded between two numbers. Here, x is unbounded. It's anything less than 0. Okay, it's from 0 to negative infinity, all the way to negative infinity. But this one is constrained between two endpoints, 0 on the left, 3 on the right. So I'm going to use those values to figure out what's happening between those two values. Now there's no input here for this piece of the function, so no matter what value you choose for x, the output's always going to be 1. Now at this endpoint here, we're going to use a closed circle because x is greater than or equal to 0. We already have an open circle there. Now we're going to put a filled in circle. And then 3, 1 I'm going to put an open circle there because x has to be strictly less than 3. It does not equal 3 for this piece of the function. So what that's saying is x starts at 0, x goes up until 3, but it does not equal 3. That should be an open circle. Now, for this piece of the function, if we make an input-output table, x can be greater than or equal to 3, so we're going to begin at 3. 1/3 of 3 is 1. 1 minus 2 is negative 1, so 3, negative 1, and we're going to put a closed circle because x is greater than or equal to 3. Now, the next value of x I choose just needs to be greater than 3, so it could be 4 or 5 or anything greater than 3, but because we need to take 1/3 of that x value, I'm going to choose 6. It's easy to take 1/3 of 6. 1/3 of 6 is 2. 2 minus 2 is 0, so 6 comma 0. And there's our piecewise function. Now there's another couple of pieces to this, part B and part C. We need to evaluate the function when x equals negative 3. Now, what I've seen in the past from some students is taking the negative 3 and plugging it into every single piece and getting 3 different outputs. But you need to remember that this represents a function. It's a function f. A function, if you have one input, has to have a single output. One input, one output. If you plug this input into 3 different pieces, you're going to get 3 different outputs, making it not a function. So we got to figure out which piece specifically this fits. Negative 3, if we look, only fits into this domain where x is less than 0. So negative 3 goes in place of this x. Negative 3 plus 1 equals negative 2. Now f of 0, we got to figure out which piece that falls into. It's this piece right here where x is greater than or equal to 0. This is where that is going to be. But the only option for an output is 1. So f of 0 is equal to 1. Okay, second page, find f of 1. What this is asking is find the value of the function f when x is equal to 1. Now this is the function f right here. This graph represents the function f. We need to find the value along this graph when x equals 1. Here's where x equals 1 right here. So the value of f when x equals 1, according to that point, is 2. Now, the domain and range of the graph, another word for domain are your set of inputs. You can determine your set of inputs kind of based on your set of outputs as well. If it's an input, it's going to have an output. Okay, and outputs are points on the graph. All of these points represent outputs. So if we take a look, for example, at negative 5, negative 5 doesn't have any corresponding outputs on the graph. Therefore, it's not an input, it's not in the domain. Neither is negative 4 or negative 3 or negative 2. But once we start at negative 1 as an input has an output at 0. Or 0 as an input has an output up here, it's 3. 1 has an output of 2. 2 has an output that's way up here on the graph somewhere. If I begin at negative 1 and go all the way to the right on the x-axis, I can go all the way out to positive infinity. And if I go up high enough on the graph, I'd be able to find an output there. So the domain, using integral notation, begins at negative 1 to infinity. Now, if you consider your set of inputs, okay, what is the set of outputs that matches this set of inputs? For example, if x is negative 1, okay, what's y, or what's in your range? 0 is in the range. Okay, 0 is the smallest number in the range. None of these y values down here have any corresponding x values matching up with them. But starting at 0, that has an x value of negative 1. Or 2, y equals 2 has an x value of about negative 0.75. All the way up on the y-axis to positive infinity, so the range starts from 0 to infinity. Now, intervals in which the function is increasing or decreasing, you only use x values. Only use x values for this. So if you take a look at this piece right here, starting at the x value of -1, okay, from left to right, if you look at this graph, the y values are increasing, they're getting larger. Okay, so for which x values is that true? Okay, between -1 and 0 right here, all of these x values, okay, represent an interval where the y values are increasing. So an increasing interval is between -1 and 0, and there's another increasing interval. Take a look starting here all the way up to infinity. Starting here, the y values begin to increase, they get larger. So the x value where that starts to happen is 1, and it continues to increase as x approaches infinity. So from 1 to infinity. These do not represent ordered pairs. -1, 0 is not an ordered pair. It's not a location on a graph. It's an interval of x values from -1 to 0. Now decreasing, the only decreasing interval is, this is the portion of the graph where the y values are getting smaller. If we look at its corresponding x values down here on the x-axis, okay, corresponds to the x values between 0 and 1. Okay. F, an open circle, you need to make a distinction here between this open circle and a closed circle. Open circle means composition, f of g of x, not to be confused with a closed-in circle, which means multiply. We're not multiplying two functions, we're composing two functions, which means the g of x function acts as an input, and that input goes inside of the f function. Okay? So since the f function is the function that's receiving the g function, I'm going to take a look at the f function here, and anytime there's a spot for an input, I'm going to turn that into an empty parenthesis. So 2 empty parentheses squared plus 1. The x acts as an input, so it becomes an empty parenthesis, and inside the empty parenthesis goes g of x, which is 3x plus 1. Now we just need to simplify this. 3x plus 1 squared is 3x plus 1 times itself. And if you multiply 3x plus 1 times 3x plus 1, you get 9x squared plus 6x plus 1. And then if you distribute the 2 and combine like terms, we're going to get 18x squared plus 12x, and then 2 times 1 is a 2. When you add the 1, you get a 3. Now g of f of x, also written this way, means now that the f function is going inside of the g function. So the g function this time is the function that's receiving the other function. So I'm going to turn this x into an empty parenthesis. So instead of 3x plus 1, I'm going to say 3 parentheses plus 1. And f of x goes in the empty parenthesis. And distributing combined like terms will leave us with 6x squared. 3 times 1 is 3, plus the other 1 is 4. Okay. Now, best way to approach these, I think, is to choose values on the graph of f of x, and find the location of those points and write them in a table. So these points I've labeled, and write their locations down. Starting from left to right, we have -2, 0, -1.5, -2, -1, -0.5, okay. Now we need to remember what each of these transformations does to the original graph of f of x. This transformation here, this 2 is inside of a function. Okay, there's a couple of things we learned about a transformation being inside of a function. First of all, it's opposite. It has the opposite effect. Here, the 2 is multiplying the x. The opposite of that would be dividing. Okay, and transformations that occur inside the function have a horizontal effect, which means it's changing the x values. So the x values here are divided by 2. So if we made a new xy input-output chart, we're going to base it off the original chart that we have made here, except all the x values need to be divided in half. So the negative 2 becomes a negative 1, negative 1.5 becomes a negative 0.75, and then negative 0.5, negative 0.25, and so on. And the y values remain unchanged. Now I didn't really provide the best graph here, I'll admit. You can always feel free to change the scale. If you take a look at our x values, they are from negative 1 to positive 1 with a bunch of small numbers in between, a bunch of small decimals. So I'm going to actually change how this x-axis is labeled. I'm going to call this negative 1/2, negative 1, positive 1, and excuse me, this is 1/2, and that's going to be 1. I'm going to call this 1, 2, negative 1, negative 2. I think it'd be easier to graph this way. Now just plot the points, negative 1, 0, negative 0.75, negative 1/2, 0, Now the effect this is supposed to have is a horizontal compression. It doesn't appear to have been compressed horizontally, but if you look at the original graph, it spans from negative 2 to positive 2. This graph spans from negative 1 to positive 1, so it has been compressed horizontally. It's just we changed the scale of the axes to make it easier to graph. Now for part B, this transformation here occurs outside of the function. Those transformations affect y values. Since it's not inside of a function, we don't have to do any opposite operations here. What this is saying is take 1/2 of the f of x values. The f of x values are the same as the y values. So half of the y values. So do that and make a new chart. We're going to use the same x values this time as the original function. But the y values will be cut in half. And I'm going to change the scale again. It's supposed to be 1, 2, negative 1, and negative 2. I'm going to change this to negative 1, and negative 2, positive 1, positive 2. And this acts as a vertical compression because the y values got cut in half, so it's got smashed or compressed vertically. Okay, question 6. It says use synthetic or long division. You really actually don't have a choice. You must use long division because your divisor, x squared minus 2, in order to use synthetic division, the divisor has to be linear. And this divisor is a quadratic. X squared minus 2 is a quadratic, so we have to use long division. Now long division is set up with the dividend inside of a fraction bar and a divisor here on the outside. The divisor and the dividend, if you look, are both missing terms. The divisor is missing a linear term, so I'm going to put in a 0x as a linear term, and the dividend here is missing a quadratic term, x squared. So make sure to put that placeholder in as a 0x squared. Along division, you're focusing on leading terms going into leading terms here. So x squared into 2x to the 5th can go 2x to the 3rd times. So 2x to the 3rd multiplied throughout the divisor is going to be 2x to the 5th plus 0x to the 4th minus 4 x to the 3rd. Draw your line, change the signs. Leading term there cancels, which is what is supposed to happen. 4x to the 4th plus 0x to the 4th is 4x to the 4th. These terms also cancel. Now let's drop down. Now notice how I'm keeping these lined up in columns according to the degree. Okay, that makes things a lot more manageable to organize. Now x squared into 4x to the 4th is 4x squared. So 4x squared times x squared is 4x to the 4th plus 0 x to the 3rd minus 8 x squared. Draw a line, change signs. That cancels. There's nothing here to add. Here we have 8x squared. Now the division is only going to occur one more time because we have an x squared going into an x squared. So this is the last time we're going to have to perform the division, because once we reach here a degree less than the degree of the divisor, we can stop. But since we have two more terms here to drop down, I can drop down both of them. Now x squared into 8x squared is 8 multiplied through draw your line, change the sign, cancels. Negative x plus nothing is negative x. Negative 5 plus 16 is 11. This is your remainder. So p of x, when it is divided by d of x, results in a quotient of 2x to the 3rd plus 4x squared plus 8 with the remainder Okay, that'll finish up part 1.